Hello friends, I am Professor Jagadeesh Hugar. So in this video, I am going to explain how to solve the problems on optimum design. So let us see the first problem. Design a tensile bar of length 200 mm. So length of the bar is 200 mm to carry a tensile load of 5 kilonewton. So it should carry the load of 5 kilonewton for minimum cost. Out of following material, use the factor of safety FOS equal to 2. FOS is 2. So here we have to design the bar of length 200 mm and load carrying capacity should be 5 kilonewton, but for minimum cost. So here optimization parameter is cost, which we need to make it minimum by using following materials. So here different materials are given: steel, aluminium alloys, titanium alloy, magnesium alloy. So here we need to select that material, so which will lead to the minimum cost of the tensile bar. So our main aim is to design the tensile bar, means to find its cross sectional area by minimizing the cost. So our aim is to find the area by minimizing the cost. So first step is to form the primary design equation. So what is primary design equation is? Here it is what we need to optimize. So here we need to optimize this cost. We need to minimize the cost. So total cost is given by cost per unit weight into mass. Mass is given by volume into density. So here rate is given, material rate is given per Newton. So that's why, so we are going to, that total cost is given by cost per unit weight, that is per Newton, into total weight in Newton. So here it is a total weight. So this is a mass multiplied by G, so that will give the weight. Okay, so this is cost per unit weight into total weight, it will give the total cost of that particular part. So this is the main design equation, that is primary design equation. So next is secondary or subsidiary design equation. Subsidiary design equation is, so stress induced in the bar is given by sigma is equal to P upon A. P is the load and A is the cross sectional area. And third one is limiting equations. So what are limiting equations? Stress should be less than or equal to, so SYT upon FOS, that is yield strength upon factor of safety. So now what we need to do is, we need to substitute these equations in the primary equation, primary design equation. So both subsidiary design equations and limiting equations, so we have to substitute in the primary design equations. So how to substitute these equations? So let us see. So this is primary design equation, that is PD, that is Cm is equal to C into rho into A L into G. So secondary equation is given by sigma equal to P upon A. So here we can write A is equal to P upon sigma. So this A value we can substitute in this primary equation. Okay, that means A, instead of A you can substitute P by sigma. And again sigma value from limiting equation, sigma is equal to what? Sigma is equal to SYT upon FOS. So again we can substitute, instead of sigma, SYT upon FOS. If you substitute sigma value, then we are going to get this final equation, that is total cost is equal to Cm is equal to C into rho into FOS into P divided by SYT into L into G. So here next step is, so this is the substituting the subsidiary equations and limiting equations in primary design equation. Okay, once you complete this, so next step is to separate the equation into, that is, three types, that is functional requirement parameters, material requirement parameters, and geometrical material parameters. Okay, so here, so what is our important thing is material parameters. Why? Here we need to select the material, so which will leads to the minimum cost. So that is, selection of material lead depends on to minimize the cost. So that's why, so we need to separate the material parameters. So this is what equation we got in the from the previous slide. Okay, so here what are the material properties in this equation? So material properties, so that is parameters related to the materials are rate of the material and its density of material and strength of material. So other things are not depends on the material. FOS is not depends on material. P is the force applied, not depends on the material. Length is not depends on material. G is a constant. So that's why material properties are C, rho and SYT. So you write separately C into rho upon SYT into, so remaining parameters you write it separately. So this parameter, so this is called MSF, that is material parameters, material separation parameters. So MSF is equal to C into rho divided by SYT, C into delta. So here it is, instead of rho, delta is used. So both are same, both are used for density. Okay, so this MSF value we need to calculate for all the given materials. So how many materials are given in the problem? So there are 5 materials are given in the problem: steel, aluminum alloy, titanium alloy and magnesium alloy. Density is given, material cost is given per Newton, and yield strength is given. So from the previous slide we got MSF equation is given by C into delta divided by SYT. So this value we need to calculate for all the 4 materials. And here we need to identify which one is the lowest one, so that cost of the tensile bar will going to reduce. Suppose if this value reduces, so automatically, so total cost of the tensile bar will going to reduce, because this is directly proportional. Okay, so that's why we need to select that material, so which is having the lowest MSF value. So here steel is having the lowest MSF value, that is material separation material value. Okay, so next, once you identify the material, so which one you need to select, so that the cost of the tensile bar will be minimum. So use the parameters values of that material, that is density, material cost and yield strength, to find the dimensions. So here sigma is equal to P upon A. Sigma is SYT upon FOS. SYT given is for material which we have selected is 130 divided by 2, it will be 60. So you substitute sigma value 60. P is already given in the problem, that is 5 kilonewton. So substitute in this equation, so you will get the area, that is area is equal to 76.923 mm square. 76.923 mm square. Okay, so this is the design of tensile bar for minimum cost from the available materials. So here we are not just done the design. So here we have done the optimum design. So here we can also use the aluminum alloy to design this tensile bar. We can also use titanium alloy. We can also use magnesium alloy. So there are 4 design solutions we can get here. But optimum design solution is this one. So when you use the steel as a material, so we can make the optimum in terms of the cost involved. Okay, so this is the first problem. So next, let us see the second problem. So design a shaft for minimum weight. Design of the shaft for minimum weight. Design a shaft for minimum weight. It transmits a torque 900 Newton meter. So required torsional stiffness, so which is also called the rigidity, is 90 Newton meter per degree. So torsional stiffness or rigidity means it is torque upon angle of twist. Okay. So using maximum shear stress theory of failure, use the factor of safety is 1.5. So here we need to design the shaft for minimum weight. So here weight minimization is the optimization parameter. So this is the parameter which we need to consider for optimization. Okay. So these are the materials given in the problem. Total 4 number of materials are given and its properties are given. So its density is given, modulus of rigidity and yield strength, and material cost is given in terms of the rupees per Newton. So here our aim is to design the shaft, means to find its length and diameter or cross sectional area by minimum, so that weight will be minimum. Okay, so first thing is what we need to do. We need to form the primary design equation. So here what we need to optimize? Weight. So that's why weight equation is the primary design equation. W is equal to, how to calculate the weight? Mass into G, acceleration due to gravity, M into G. M means rho into V. Rho is density and V is the volume. Again, if you write in instead of V, if you write area into length, because it is a shaft. So volume of the shaft is given by area into length. So this will become rho into A into L into G. Again, instead of area, if you write pi by 4 into D square, so again you can write, so rho into pi by 4 into D square into L into G. So secondary equation. So all this stress induced torque, so forces, so they will come under the subsidiary equations or secondary equations. So this is torsional equation. So everyone we know. Okay. So these are the equations formed from this primary equation. Sorry, from this equation. So this is derived. So that is, if you consider T by J is equal to G theta by L, and next is T by J equal to tau max by R. So here T is torque, J is polar moment of inertia, tau max is maximum allowable stress, R means it is radius of the shaft, G is modulus of rigidity of the shaft, theta is angle of twist, L is the length of the shaft. So from this equation is written. So here J is substituted as a pi d raised to 4 by 32. So if you substitute pi d raised to 4 by 32, then so we can get this equation, that is L is equal to pi g into d raised to 4 divided by 32 into q. Q means it is, instead of T by theta, Q is substituted. Okay, so from this equation is derived. So instead of R it is d by 2, diameter upon 2, it is radius. R is equal to d upon 2, J is equal to pi d raised to 4 upon 32. So if you substitute that, we are going to get this equation. Okay, so these are the secondary equations, secondary design equations. And next is limiting equations. What is limiting equation? Is stress should be less than or equal to, this is shear stress in tension. So this is shear stress. Okay, so this is not tensile stress, so this is shear stress upon FOS. So this is given by 0.5 into yield stress in tension. So we shall see it later on how to calculate this value. Okay, so this is the equation we got from the previous slide, that is weight. Instead of L, so we are substituted the L value in this equation. Once you substitute the L, so we are going to get this equation. And dq also, d also we have got in the previous slide. So that is d is equal to, suppose if you take this on right side, it will become 1 by 3. Okay, so value of d substitute here, so d raised to 6, and this is 1 by 3, so it will become square 48 into t raised to t divided by pi into s by t square. So remaining these parameters will be as it is and g as it is. Just substitute the value of d in this equation. Okay, so this, we will get this equation. Afterwards, so substitute the values except material values. So substitute value of, so this is constants pi by 4, and substitute value of q, that is whatever given in the problem. So how much the value of q is given in the problem is q is 90 Newton meter per degree. Okay, so substitute value of q and substitute value of t. Okay, substitute value of g except rho, g and syt. Substitute all the values, then we are going to get this 162. So calculate all the values, so we are going to get the 162 into rho g upon syt square. So this is the MSF. This is depends on the material factors. Okay, so this is material requirement, this values totally depends on the material. So here these values need to be substituted. Value of these values should be selected from material, so which will leads to the what, minimum weight. So these values, that is rho, g and syt, that is density, modulus of rigidity and syt, we need to select of which material, so which will leads to the minimum weight reduction. Okay, so that's why these values have to be calculated for different values, and we need to select whichever the minimum value, we need to select that material, so which is having the minimum MSF value. Okay, so this is the table given in the problem, that is material, density, g and yield strength. And next we need to add one more column here. So MSF is equal to delta into g by syt square. So instead of rho, delta is used, for density delta is used, so into g divided by syt square. So if we calculate, so we are going to get these values. So here, so values are substituted in this formula, that is rho is substituted as it is, that is density is substituted as it is. Next, modulus of rigidity is substituted into 10 raised to 9, because GPA 40 into, suppose let us say example for M1, rho is 8500, delta is 8500, into g value is 80 into 10 raised to 9. So here it is substituted in terms of the Newton per meter square, so it is also in meter cube, so that's why, so it is in meter square, so that's why you need to multiply by 10 raised to 9. Afterwards, yield strength is substituted in terms of 130 into megapascal, means into 10 raised to 6. So if you substitute like that, so we are going to get this values. So here we need to select, we need to identify which value of MSF, which MSF value is minimum. So this is it is minimum for material number 3. Okay, so that's why we need to select this material for the design, so that the weight of the shaft will be minimum. Okay, so selecting this material number 3, you can find the diameter. So to find diameter, we need the torque and allowable shear stress. Torque is given in the problem, so allowable shear stress is given by, so 0.5 into shear stress in tension, that is for selected material it is 90, 0.5 into 90 by factor of safety given is 1.5. So allowable shear stress value is 30 megapascal. So if you substitute this 30 in this equation, so we are going to get diameter is equal to 53.46 mm. And again, so if you want to find the length, so again this substitute in this length equation, so which is already we formed in the previous slide. So you will get the length of the shaft. G is modulus of rigidity, which is equal to 40 into 10 raised to 9. So again, if you want to substitute values in meter, you substitute all values in meter. If you want to substitute in mm, all values substitute in mm. So don't get confused in the units. Okay. So substitute value of D, that is 53.46, and Q is 90. Okay, so you can see here, so this is in Newton meter per degree. Okay, so here you don't get confused. Substitute all the values, so you will get the, so length is equal to 6220.289 mm. So this is, suppose if you want to reduce the cost from the same problem. So in this problem, what we have done is, so we have found these dimensions for minimizing the weight. Suppose if you want to minimize the cost, so cost equation, what it is, weight of the material, total weight of the material into cost per unit weight. So this W equation already we got in the previous slide from previous problem, that is for minimizing the weight. So this, which is given by 162 into rho into G by SYT square into cost of the material. So just again find the value of total cost for all the materials and select the value and look for the value which is minimum. So for here, for M1, if you select the first material, so cost of the what you can say, this cost of the shaft will be minimum. So that's why selecting the first material, and if you make design calculations, so your cost will be minimum. So in this case, so we are going to get the diameter is 47.293 mm and length is 7619.25 mm. Okay, so next let us see problem number 3. Design a problem number 3. Design a thin wall spherical vessel for maximizing the gas storing capacity under pressure. Pi is equal to 4 megapascal. This is the, so it should be the capacity of the spherical vessel, that is Pi internal pressure, that is design pressure is equal to 4 megapascal, and thickness is very less than diameter. T is wall thickness and T is the mean diameter of the vessel. Factor of safety here it is 3. Mass of the vessel should be less than or equal to 125 kg. So it is a limit is given, not a specific value. Okay. So it should be less than 125, it may be 120, it may be 115, like that. It should not be more than 125. So design the pressure vessel with objective of maximizing the gas storage capacity. So here optimization parameter is to maximize the storage capacity, gas storage capacity. So here these are the materials are given, 3 materials, and its properties are given. Its density is given and its ultimate strength is given. So formula required here is mass of the vessel. Mass of the vessel is given by, so its density into its volume. So density into you can see here. So density, that is rho, volume is given by pi d square into t. So this is equation for the mass of the vessel. Stress induced is given by, in case of the spherical pressure vessel, so it is given by P into D divided by 4 times T, where P is the inside pressure, D is the diameter, mean diameter, and 4T, that is 4 times thickness. So here we need to find the dimensions of this spherical pressure vessel, that is D and T, with maximizing the storage capacity. Storage capacity means, so it's volume. Okay. So next is, what is the first step is to form the primary design equation. So what is, which parameter we need to maximize? It's volume. So that is the become the primary design equation. Volume is equal to, so volume of this sphere is given by 1 by 3 into pi d cube. Okay. So subsidiary design equations are, it's stress and mass. Okay, stress is given by P into D into P into D divided by 4 times T, and mass equation is given by M is equal to rho into pi into D square into T. So here you can see, here D is there. Suppose if you want to substitute any values, secondary equations in primary equations, so we have to form in terms of D. D is equal to, okay, so that's why, so here you can see, so D is equal to, you can simplify this in terms of D, so you are going to get this equation, and here we are going to get in terms of T, and you can substitute T here. Okay, so otherwise you can substitute, you cannot substitute D here because we required in terms of D. Okay, so substitute T value here, and whatever you are going to get this equation, so that you need to substitute in the primary equations. Okay, so next limiting equation is, mass should not be less, should be less than or equal to 125 kg, and sigma T should be less than or equal to SUT upon FOS. Okay, so next step is to substitute these equations in primary equations. Okay, so this is primary design equation, this is subsidiary design equation, and these two are secondary equations. So substitute these equations in primary equations. So we are going to get the equation, that is V is equal to M into sigma T divided by 3 into Pi into rho. M is the mass, sigma T is the, so stress induced, and Pi is the internal pressure, and rho is the density. So this is the primary design equation. Okay, so these are the limiting equations. Okay, so here what is final equation, primary design equation. So you substitute whatever the values except which are material properties. Suppose mass, so this is should not be more than 125, substitute 125 value. So Pi is given, substitute that value. So Pi is given, substitute that value. So then we are going to get in this final PD equation in this form, that is V is equal to 6.944 into 10 raised to minus 6 into SUT by rho. So these values should be substituted for material which will leads to the maximizing this value. So that's why this is the maximizing parameter. So this is the maximizing parameter, that is SUT by rho. So that is SUT by rho is the MSF here. So this value we need to calculate for the different materials. Okay, so we have to select that material, so which will maximize this value, because it will increase the storage capacity of the pressure vessel. Our aim is to maximize the capacity of the pressure vessel. So let us see, these are the materials given in the problem. So you calculate this MSF value for all the three materials and identify which one is having maximum value. So MSF is maximum for the material number 2. So that's why select second material for design of the pressure vessel.